Bohr Model. The atomic energy levels of a hypothetical atom can be determined by the following formula. E sub n is minus 24 eV over n squared. What are the energy levels n equals 1, 2, 3, and 4 of this atom? Draw the energy level diagram of the atom. What is the wavelength of the photon emitted when an electron moves from the n equal 4 level to the n equal 3? Would the emitted photon be visible? Starting from the n equals 3 level, what transitions could the electron make next? Draw these on your diagram. If the electron were at the ground level, how much energy would be required to remove it from the atom? What are the energy levels for n equals 1, 2, 3, and 4 of this atom? Well, this is pretty straightforward. We've got the equation. Put in your values for n in the denominator and make sure you square it. And we have the 4 energy levels, starting at E sub 1, negative 24 eV, up to, or down to, negative 1.5 eV for E4. Draw the energy level diagram of this atom. Energy level 1 should be at the bottom. That's the most negative. That's right over here. With higher levels above. The levels should not be evenly spaced. The change in energy between levels 1 and 2 is the greatest. That's this distance here, which as you subtract these two, you find that's what, 18 eV? With each successive transition having a smaller change in energy. So let's look at the 4 to 3. That's going to be 2.67 minus 1.5. So what is that? 1.27. So that's between 4 and 3. That's very small. A lot smaller than 18. The dashed line up at the top for n is equal to infinity, that's going to be our highest possible energy level. What is the wavelength of the photon emitted when an electron makes a transition from the n equal 4 level to the n equal 3? Okay, so it's going to a smaller energy level. The electron is, so that energy is released with the photon. So we have our two energy levels for 4 and 3. The difference in energy is E final minus E initial. So it's minus 2.67 eV, that's the third energy level, minus a minus 1.5 eV. So the change in energy is negative 1.17 eV. Now that's the energy that was lost by the electron. That was used to form a photon. The photon gained the energy. The energy lost by the electron goes into the photon because energy is conserved, and we get 1.17 electron volts. What is the wavelength of the photon emitted when an electron makes a transition from the n equals 4 level down to the n equals 3 level? So what's happening there is the electron is losing energy and energy is conserved, and a photon will be emitted with the same energy that the electron is losing or transferring to the photon. So here's our energy of the photon, and we have E is equal to HF. F is equal to c over lambda, and h, of course, is Planck's constant, so the energy of the photon is hc over lambda. Lambda is hc over E. All right, we just switch these two things. So our wavelength of this photon is going to be Planck's constant. Use eV seconds because our energy is in eV. Speed of light, and here we go. Here's the energy of the photon. So the wavelength of this photon is 1.06 times 10 to the minus 6 meters. Now we'd like to get that in nanometers. Nanometers is 10 to the minus 9. So we want to decrease this by 3. Decrease the exponent by 3. So that means we move the decimal place 3 to the right, and then we get 1060 nanometers. Would the emitted photon be visible? There's no way we expect you to remember this, so you'd have to look up on a chart or in your homework or in a textbook. The visible range of light is about 400 nanometers, which is violet light, to 750 nanometers, which is red. This wavelength is a bit longer than the red, so it would be infrared light, which we can't see. Starting from the n equals 3 level, what transitions could the electron make next? Draw these on the diagram. Electrons can only move to lower energy levels on their own. They need to be hit by a photon to move upwards. So the electron can go straight from 3 all the way down to n equals 1, or it can go from 3 to 2, and then 2 to 1. so we have 3 transitions it can make. If the electron were at the ground level, which is n equals 1, how much energy would be required to remove it from the atom? In part A, we calculated the ground state energy, E1, was negative 24 eV. This means that the electron is bound to the atom with an energy of 24 electron volts. So if we wanted to remove the electron from the atom, we would have to apply that same amount of energy, 24 eV.